Hey everybody, today we are going to start our final function that we're going to study in Algebra 2 over log functions. And this is a great place to end up on because it is the inverse of exponential, which is the function that we were just studying in our last unit. So I want to make the connection for you first. I want to show you the new function, log function, and how it relates to exponential. So let's begin with what we studied last week. This is an exponential function with a base of 2. Remember, this number can be any number. 2, 10, and e come up the most, but we can have any number here for the base. The key to an exponential function is the x is up there as an exponent. That's what makes it an exponential function. Over here, you can see the graph of that equation right here. 2 to the x, this is what the graph would look like. And so let's look at the features here. First, let's look at the domain. Well, this is going all the way left and all the way right, so this is a domain of all real numbers. Our range, however, is getting closer and closer and closer to this x-axis, but it is never going to cross it. How I want you to think about it is if I say take 1, okay, and half it. Well, if you half 1, you get a half. If you half it again, you get a fourth, and then you get an eighth, and then a 16th, and then 32nd, and then a 64th. And if we keep halving and halving and halving, are we ever going to reach 0? We never will. We can half numbers on into infinity, but we will never be exactly 0. So that is why our range is from 0 to infinity, but it doesn't include 0. That's why I put a parenthesis. Remember, that means everything right up to 0, but not including 0. And of course, we never include infinity. Because of this phenomenon, we have a horizontal asymptote here at y equals 0. It's cutting through the y-axis at 0. And we also have a y-intercept there at 0, 1. All right, so now let's compare that to our log function. This is going to be our new function. It is the inverse of an exponential. So keep in mind, anytime we want to find the inverse, we can always just switch these x and y coordinates and see the new function. So I'm going to take 3, 8, and when I flip it, it will become 8, 3. And 2, 4 will become 4, 2. This point right here is 1, 2 will become 2, 1. And 0, 1 will become 1, 0 right there. And negative 1.5 will become 0.5, negative 1. And we can continue flipping these points, and we can kind of see the graph forming right here. It's going to get closer and closer to the y-axis, but again, it's never going to reach it, just like it doesn't reach the x-axis here. So for logs, we actually have a vertical asymptote at x equals 0. Because it's getting closer and closer, but it's never going to reach it for the exact same reasons as the exponential. So our domain, we're asking how far left and right it goes. Well, again, this is going to get close to the y-axis, but never reach it. So it's going to go from 0 to infinity, but not equal to 0. The range, how low does it go? Negative infinity to positive infinity. So again, this is going to be all real numbers. We have a key point right here, an x-intercept at 1, 0. So I want you to look at the connections of these two functions. These two functions are inverses of each other because they reflect over the line, y equals x, as all inverses do. And the x and y coordinates have been switched. Just like all inverses that we studied this year. Those are the relationships that they have. What do you notice about the domain and range? Well, the domain and range are also switched because the x and y values are switched. Also notice that the x and y intercepts have a relationship. We have a key point here at 0, 1 and a key point here at 1, 0. And same thing for the asymptotes. We have a horizontal asymptote. Therefore, in the other function, we have a vertical asymptote. So now that you understand that they have an inverse relationship, I want you to keep that in mind today. The reason that is key is because next section, we are going to be solving equations, exponential and log equations, And now you know that logs are how we undo exponentials. So when we're solving equations, as we've been doing all year, if you have an equation that is like this, I say, okay, how do you undo this? How do you get x by itself? And you guys will say, Miss Maneri, you're going to divide by 2. Why are you dividing by 2? Because right now it's multiplied together. To undo it, we know that multiply goes with divide. That's how we undo it. And if we had an addition operation, we would undo it by subtraction. And if we had a square to undo it, you would say, well, just take the square root of both sides. Well, now we know when we have an x in the exponent, to undo that, we are going to use logs. So now we know how to undo that, and we're going to be using that more in our next section. Today, your goal is to be able to understand how to go back and forth from log form to exponential form and vice versa. So that's the core of what we're going to practice today. So look at, this is a setup for an exponential function. B is our base, whatever is the base of that exponent. X is the exponent, and A is what this equals, whatever the solution is, okay? When we rearrange this into log form, this little subscript number, the number that's right below the log, is called the base of the log. So look at this. The base of the exponent becomes the base of the log. So the base stays the base when we rearrange it to the other form. Because logs always answer the exponent, the log should equal this exponent because it's the solution for it. And this piece right here is called the argument. So that is what you're taking the log of. All right, so we are going to practice rearranging a few, and then I'll come back to the special cases. So if I want to rearrange this one, for example, I want to arrange this into log form. The base of this exponent is going to become the base of the log. So the base stays the base. Remember that a log always answers for the exponent. So it is going to equal 5 because that's how we undo it. And then 243 is going to be the argument. So that is how you would range from exponential form to log form. Now let's go the other way, from log form to exponential form. The base of the log is going to become the base of the exponent. Remember, the answer to a log is the exponent. So that's going to become the exponent is going to equal 36. All right, one last rearrange. So the base of the exponent becomes the base of the log, so that's the subscript. A log always answers the exponent, so it should always equal the exponent, and S is the argument. Okay? Try the next one on your own. I'm going to give you a minute to think about it. Did you get it? Base stays the base, and the others switch place. Base stays the base, the others switch place. Last one. So log, base stays the base, the others switch place. Now today we're also going to be evaluating logs. So I want you to notice here that if I didn't know what this equaled, here's what you're going to be thinking. 4 to what power is going to equal 64? That's what a log means. That's what it's asking. Well, 4 to the third power equals 3. So that's how that log is going to work. Okay, we're now to our first special case. Notice this log has no base. The base, if it is not there, is always implied to be 10. So this is special case number 1. Whenever there is no base, 10 is always implied. It's kind of like in the last unit, whenever we had a square root, we knew a 2 was implied there if there was no number there. Otherwise, it would tell us what the root was. So this is true for logs as well. Also, you probably have noticed that there's a log button in your calculator. Whenever you push this log button right here, that is implied a base 10 because base 10 is one of the most common ones, and so that is implied. So when I want to rearrange this problem right here, when there's no base, I know that 10 is what is implied. It equals the exponent, and b is going to be what it equals. All right, so again, this one is just to rearrange like we've been doing. Base of the exponent is going to become the base of the log, and the exponent is what we are solving for when we rearrange it. Okay? This one is the same kind of problem. Base stays the base, so the base of the log is going to become the base of the exponent. T is the exponent, and S is what it will equal. All right, I want you to think about this one again. 2 to what power is going to equal 1/16 if we didn't have this -4 here, because that's the answer. I'm trying to help you think through this. So 2 to the 4th power is 16, right? 2 times 2 is 4. 4 times 4 is 16. Okay, so 2 to the 4th power is 16. Now notice, because it's a fraction, we want the reciprocal. That's why it's -4, because 2 to the -4th power is 1/16. Okay, here's our last special case. This e is not a variable. E in exponential functions is actually a constant. E is approximately 2.71. It's an irrational number though, so it goes on and on and on, okay? Think of it as like pi. You know pi is approximately 3.14159, and it goes on and on and on, right? The reason they came up with pi is because they realized it came up a lot when we were talking about circles. And so they had to give it a value, pi. They call it pi. E is the same kind of scenario. It comes up a lot whenever we're compounding continuously. So, for example, when we're talking about population growth, you may have seen the equation P times E to the RT power. P would be like the initial population. E is that constant, 2.71. This is the rate, and this is the time that are both exponents. So this is a formula that you can use when anything is being compounded continuously. We know that as soon as another baby is born, they're added into the population, and then it continues to compound. Nowadays that we have computers to do our banking for us, E comes up when we're banking too, because they continuously compound. So I want you to keep in mind, E is not a variable. It is a constant. It is 2.71 and on and on and on. You can find E in your calculator. There's 2 places. There is E right here. So if you put E, and this automatically brings up an exponent. So E to the 1st power would be E. So that's 2.71828, and it goes on and on. Okay, we know it doesn't even stop here where the calculator ends. There's another E button on the divided by. So if you hit second divided by, E also comes up there. So that is what E is. It is a number. Math teachers always kind of joke that we should teach kids to count 1, 2, E, 3, pi, 4, and on and on and on, because we want kids to know that it's just another number. Because it comes up in mathematics a lot, they gave it a certain notation, that E notation. Now, keeping that in mind, for our log conversation, because E comes up so much in exponential functions, they came up with a very special log for E, and it is called ln. But this means natural log. Natural log, okay? So anytime you see log base E, we will instead write it as ln. We never write log base E. You will never see that in any math textbook unless it's telling you that it equals ln. So always replace log base E with ln. So I'm telling you that because we're coming down to a problem now that we need to use that. We have a base of E here. So instead of doing log base E, I'm going to do natural log. And it's the natural log of 9 equals my exponent of x. And we actually could evaluate this in our calculator. There is an ln button. You see it, it's right below log. And you can do the natural log of 9 to get your answer right there. Okay?